Hi, I'm Neven Miculinic. So briefly about me. I started programming when I was 12. First with some algorithm competitions in Logo and Pascal. Later on, I did various projects. My first experience in real, complex systems was during university when I was a Facebook intern. Later on, I did some DNA-based coding using machine learning and deep learning. And for the past 2 years, I've been mostly focused on Kubernetes and cloud-native ecosystem. I built services running on it, operated Kubernetes clusters, and written Kubernetes operators. Currently, I'm employed at Luce, which is a cloud-native platform company which offers various products and services to help enterprises run their cloud-native stacks on any infrastructure. For all this time, I've been interested in how things work under the hood. Since I'm mostly working on Kubernetes, Go is a natural fit for this ecosystem. So here, I'll start with a simple example of really common data arrays in the wild. So we have a counter. This counts some number of events in your system, likes, matches, number of burgers outside eaten for half an hour. And we have a function which increments this counter. But we increment it concurrently. So multiple Go routines. In other languages, it would be coroutines in Python, or you can even use native system level threads. But the main thing is, everything this function is called from multiple threads, coroutines or coroutines, whatever, concurrently. Upon finishing this function, we might get different outputs. We might get 10,000, which is what we expect, but we might also get 7,000, 5,000, 3,000, on any value in between. This is because this operation here, incrementing the counter, isn't atomic, but it's actually composed of 3 operations. Loading this variable into memory, that is into processor register, incrementing by 1, and storing it back into memory. So here is just a example. Now I want to show you some real-world consequences of data races in the wild. First one is called cow. It's pretty famous Linux kernel exploit about a few years ago. And for consequences, unprivileged user can gain root access to your machine. Other one is even more deadlier. It's called Ferrac25, which is a radiotherapy machine from the previous century. Under some pretty common scenario, if the operator is too fast in typing the corrections and modifying the machine settings, the machine's UI would get out of sync with the real machine state. So the operator will think, hey, I'm giving this guy some minimum math variation, while the machine thinks, hey, I want to make a Hulk out of him. And it ends with people dying and some accidents happening. So that's why you need to be careful. Next, let's just bring some definitions, which I'm going to use throughout this talk to help bring everybody on the same page. First, what is a data race? I mentioned a few times something called race condition. Race condition is really a generic term of some undesirable effect which might happen where some parts of your system are acting concurrently, and for proper functioning, they need to happen in specific order. Other way to call it would be unwanted observable non-determinism. But this is really domain specific. What's this unwanted part or undesirable, which is really hard for automated tools to use on their own. That's why I'm focusing on data races, which are much more clearly defined as a concurrent access to a memory location, one of which is a write. Concurrent access is another beast. So concurrent access is one where event ordering is known. In this context, event is a read or a write. There's no happens before relations between events. On this slide, you see some 2 Go routines happily living. These boxes represent some events happening. You know this event happened after this event because it's this Go routine's execution trace. But there is no event ordering between this event here or this event here. The only way to establish this happens before relations if we use some synchronization primitives, something like a channel sending or receiving in Go, or mutex locking and unlocking. We know that this event here happens before mutex locking. Also, that this event here happened before mutex locking and every other event happening afterwards. So here are some typical examples of common mistakes people do in programming languages like Go, C++, Java, but not Rust, because Rust, its type system actually prevents you doing most of these things. This is pretty common. You have a simple for loop, and you make an anonymous function and running it a separate Go routine by using the closure variable. You would expect this would write 0, 1, 2, 3, 4, but you might get 0, 4, 4, 4, 4, depending what's the execution trace between each of these 5 Go routines and the main Go routine. Fix, pretty simple, just copy the value. Other example is unprotected global. Same as the introduction example, you increment this variable concurrently by not using the atomic operations. Either guided by mutex, or you actually can use atomic increments, which is a special CPU instructions which hide away the locking for you. Underneath the hood, it logs a whole cache line where this variable is living in memory, but there's just implementation detail. And the third thing is violating your language memory model. This being too smart for your own good. So in Go, in a single Go routine, the compiler is free to do many optimizations and reordering, as long as those effects aren't visible to other Go routines, and execution happens as if it was described in the code order. So in this example, the compiler might reorder these two statements. So it could set the variable done to true before setting the variable a to hello world. It could also do load fusing, whereby it won't load this variable done each and every time of loop iteration by extracting in a special variable that is in a cache to prevent loading each and every iteration. So it's perfectly fine to do those two optimizations, and probably many more you don't even have to think about that this will break. So here are the options for synchronization primitives within your code. At least in Go, you have mutexes, and atomics in most of the languages. Most languages has either a native support like Go for channels or have some kind of library implementation for it. And now we're going to the core of this talk is how this data race detection algorithm works under the hood in Go, in C and C++, and in Rust if you want to enable it. For Go, it's quite simple. You just append a dash race flag, and the compiler will compile your code with support for data race detection. Underneath the hood, it uses something called threat standardizer version 2, which is a library, a part of LLVM toolkit, which instruments your code with additional stuff, we'll explain later. It will perform data race detection. It has found many bugs, both in Chrome, in Go, and various other products. It's kind of not cheap, because it will slow down your code 2 to 20 times, and it will increase the memory overhead of 5 to 10 times the memory your program usually runs. It requires SIGO and 64-bit operating system. The most critical aspect of this algorithm is there's no false positives. So because it trades some accuracy for performance, that might be some unlikely false negatives, but if this tool screams at you something is wrong, something is definitely wrong. It's not like, it's just this edge case, nobody cares about it, it's always wrong. And I talked about compiler instrumentation. On this example, this is a simple code being compiled or something like this for x86 assembly. If you do dash race, it serves a bunch of code here. The most important parts being runtime race read and runtime race write. That is, for each memory location you read or write, the Go compiler inserts a read memory barrier or a write memory barrier. It is okay.
It's like the old Nokia.
Yeah, it just works. Anyway. Now we're going to go into more detailed descriptions how the algorithm works underneath the hood. Now the bad stuff, because if you want to determine if some arbitrary program has a potential data race, it's kinda NP hard, So for all practical purposes, it's completely infeasible. All useful algorithms do some tricks where they trade off performance for accuracy. You have a few choices. You can make some static analysis tool by annotating your code with special annotations, or Pathfinder works like this. Or you could model your programming code in some model checker language like TLA Plus or Alloy. But all this static analysis thing takes a lot of time, takes additional training. And at the end, it's much more efficient if you just run the program dynamically. So you run any possible binary dynamically and do some analysis there. Because it's much easier to apply here things where the compiler emits the instrumentation for you, instead of you as a developer having to manually code what your code should or shouldn't do. In dynamic analysis, you can do it on the fly. So as the program is running, you evaluate, has the data race happened? Alternatively, there is also some solutions where they emit all the events which happen in the system to some external storage, and after the fact, after the program ended, they analyze it post-mortem, has something weird happen, which is a possible data race. Goes one is on the fly. And as I mentioned, there's multiple ways how to detect data races. The data race detector in Go, the threat synthesizer, uses happens before detector, which will work on these happens before edges. Other approaches include lockset base, where each memory location has like a fictive virtual lock and some thread owns it. And there is also hybrid models which combine those two approaches in the literature. So how this happens before relation works? How do you determine if this arc is okay or not, or if those two events are possibly concurrent? Implementation detail relies on something called vector clocks. So each Go routine, this is the first one, has its own logical clock. So this is event 0 in Go routine 1, event 1 in Go routine 1, event 2 in Go routine 2. By comparing their logical clocks, we can see these events are sequential, and we can establish an ordering between them. To use vector clocks means that we also extend this logical clock by remembering the last time we synchronized with other Go routines. So when we perform a synchronization, either loading a mutex or channel or whatever, we know, hey, this is in my own universe, my logical clock is free, and the last time I synced with Go routine 2 is also free. The synchronization operation is quite simple. You just take the maximum of each logical clocks per Go routine. Also, this operation is pretty much transitive. So if there was a third Go routine syncing here, it would also sync here. And it's Go routines 1 vector clock. Comparing it, those vector clocks, they form a partially ordered set. That is, some elements are comparable. If there is a happens before relation between them, we know those two happens in that ordering. Otherwise, they happen concurrently, and you have a possible data race if they access the same memory location. Now we'll come to the first algorithm which I'm going to present, which is called DGIT+. This one is a core algorithm which tracks this problem. Other ones are just improvements over the existing one. We remember the full vector clocks for the following things. So for each lock, we remember the last time each Go routine released it. We remember the last memory read time for each memory location X. Last time it was written to memory location X, and we remember the full vector clock per each Go routine. Okay. And here is some possible execution trace. So as I mentioned here, these are the events. For example, events for some memory location. They arrive to our algorithm in some ordering, so they are kind of serialized, which are approximately temporally ordered. So the first event arrived, this is Go routine 0, Go routine 1, lock M, and write location X. So the first thing that happens, we write to location X. Okay, this vector clock stays the same, nothing really important changes. There was no synchronization happening, but we update the last time we were written to this location X, to 40. We perform an unlock, which increments really important event happening, which is synchronization. And by updating here, we also update the last time this lock was unlocked with to 40, which equals to vector clock 40. We perform a locking operation of mutexm, and to get this new vector clock for go routine 1, we take the maximum of its own vector clock, 0, 8, and the vector clock for this mutex, which is 40. We perform a write, and when we perform a write, we compare this vector clock with the last time it was written vector clock and determine if these two events happen concurrently. In this case, they didn't, everything is fine, and there's no data race happening. Another example, without these synchronization primitives, we have two writes which have different vector clocks which are not comparable, so there's no happens before relation between them, and therefore you have a data race found. Okay, so here's the bad news. For each memory location X, you remember the full vector clock. If you have 100 go routines or 1,000, this is quite a big memory space. So what next algorithm found out, their improvement, called fast track, they observed the following fact. If you write to some memory location X, each write, if there is no data races, will be sequential. So there is single write, 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 write. So the only thing you need to remember for writes is which is the go routine which written, this is the go routine 0, and what was the logical time this go routine brought to it. They call this abstraction, this nice trick, a shadow word. So when the go routine 0 writes to location X, we remember, hey, check if there's a the data race. There's not, great, we can continue. And just remember, hey, the last time somebody wrote to location X was at local time 4 for go routine 0. Stuff happening, we compare, oh, go routine 1 wrote at its logical clock 8. If there is, but for reads, the situation isn't so simple because it's perfectly valid to have multiple concurrent reads happening. So they use shadow words as much as possible, and when there is concurrently reads to this memory location, they fall back to the full vector clock. For many cases, this is a big performance improvement. And the last thing, the real algorithm, the thread tensor version 2, does the following. So first, they divide your memory, virtual memory, into 8-byte chunks. So if you imagine your virtual memory, they dedicate some space for location, and they dedicate some space for this, holding this shadow whirlpool. So for each 8-byte chunks, they decide to have 4 shadow words, which are explained like, oh, hey, what subset of 8 bytes were written or read to? Was it a write or a read? And this shadow word, so which go routine performed this operation and at which logical time. So this shadow word pool is approximation of these writes and reads. They only keep the last 4 elements, and if new event happenings, they just evict any random old ones. So this is a probabilistic algorithm which could yield false negatives, but no false positives. The good thing about this is performance, because this shadow whirlpool is fixed sized. It's memory mapped in its process virtual address space, using some simple tricks like byte shifts and ends. So let's go over this example for this simple shadow word. So this is 8 bytes. First we write with 2 bytes to the first 2 of this 8-byte chunk. We perform a read, everything happens, no data race is found, everybody's happy. But now we perform a read by go routine 3. But when we compare shadow word for the read for go routine 3 and the shadow word that was written for go routine 1, we can see those two events concurrent. This because go routine 1 wrote with its own logical clock 10, but go routine 3 is reading with its own logical clock for 5 for go routine 1. So there's some data race happening. To finish the thought, in this talk, I summarize what a data race is, I cover the most common mistakes, and how Go's dash race works. However, this is not panacea. If you do something like this, you do atomic load of this integer variable, increment it, and atomic store, you would fool the data race detector. But this isn't probably something you want in your code. Thank you, and I'm now ready for questions.
Please raise your hand if you have a question. No questions? Oh, okay.
So you've shown that data structure that they use for tracking of the vector clocks, which is
These shadow words.
Yeah. So do they have one of those for each 8-byte chunks of memory, or is that global for the entire program?
So if you look at the virtual address space of a process, they have a virtual address region for allocating new memory, and they have a memory mapped region here, which is just to store shadow words. And this is for all possible allocatable chunks of memory in your program.
Okay, so they have one of those for each chunk of allocatable memory?
Yes.
Oh, okay, okay.
What's the relevance of this for Rust? Because it's in Rust as well, right?
Well, for Rust, if you do safe programming, they kill data races for you. It's amazing. If you do something unsafe, because it's compiled with LLVM, you can include the threat centers option as on, and you can test your unsafe code for potential data races.
Any other question? No? Thank you, Neven.